All right, William, can you hear me okay?
Uh, 1 second. I can hear you, but it looks like it's changed.
Okay.
Go ahead.
Can you hear me now?
All right. Yeah, we're good to go.
Perfect, thanks. All right, good morning, everybody. I hope you are doing well and had a nice weekend. So we finished our chapter 3 quiz yesterday, which means now we are moving into chapter 4. And so in chapter 4, what we're going to be doing is saying, okay, now that we know how to take all these derivatives, well, how can we use these to learn more about our functions and what's behaving and all the things that are going on? So we'll be taking our derivative as sort of a first step to then analyze functional behavior. So today we're going to start with looking at something called local maximums and local minimums. So I'm going to go ahead and switch over to the DocCam. Okay. So our goal for today is to learn about how to find what are called local maximums and local minimums. And so I'm sure you've heard the word maximum and minimum before. And so I want to caution you that there's sort of two types of maximums and minimums we're going to look at, and that the ones that we will look at next week are probably more in line with what you think of when you think of maximums and minimums, right? So maximum is usually like the highest or biggest thing, and minimums are the lowest or smallest things. We call those absolute maxes and mins. But today we're going to be looking at something called local maxes and mins, which is slightly different. Oh, did I lose you? All right, if you are streaming in, we're going to give them a minute. I think they disappeared.
Okay, I think we're back. Can you hear us okay, Adina?
Yeah, can you hear me okay?
Yeah, absolutely.
You guys just disappear?
Yeah, for some reason, I was just thinking, oh, wow, that hasn't happened in so long.
Okay, well, we'll just keep going from there and hope for the best. So let me go back to my share screen.
Last thing we heard was you just saying we're going to do maximum, and you were just about to share screen.
Perfect. Okay, so we're really interested in finding what are called local maximums and local minimums. And so these have a pretty specific definition of how we're going to look at them and find them. But we're going to talk about what they are, and then we're going to take a step back to figure out how do we find them and classify them. So we won't jump right into local max and mins, but we will get there today. Okay, so let's just talk about what they are so we all have a good idea in our minds about what we're trying to figure out. So we say that a function has a local maximum at p. So p is just some number, like at 1, at 2, at 3. If the y value at this particular value is greater than or equal to values of f of x near p. So what does that mean? That means in like a small area, this particular value is the highest value. Similar for local minimums. If you have a value that's the smallest value in a small area, we call that a local minimum. So important things about local maxes and mins. First, you can have more than one. So you could have 2 local maxes, 3 local maxes, 5 local maxes. That's typically different than when you think about a maximum being like the absolute biggest, right? How can you have more than one? Well, it's because we're looking in small areas. Okay. And so local maxes and minimums do not have to be the highest or lowest values of the entire function. So when we look for like the absolute max and the absolute min, we either call it the absolute max or the global max, and we will learn how to find those later, but that's not really what we're looking at today. Today, we're looking at local maxes and mins. And so here's a picture just to sort of give you a visual of what we're talking about. So notice here, we have a local max right here because in this little area, it's the highest point compared to those around it, right? And then our local minimums are the lowest point in sort of the area around it, okay? So notice that we have 2 local minimums here and 1 local maximum. The other thing I want to point out is if we consider the tangent lines at these points, they have something in common, right? So at each of these points, we see that we have this tangent line that's horizontal. So what that tells us is that the slope of the line is 0 at these particular points, and that's not a coincidence. So we're going to start by thinking about this idea of identifying where we have these horizontal tangent lines as sort of a first step. And then once we figure out these places, figure out, well, how do we know if it's a local max or a local min or what's going on? Okay, but visually, this is sort of what we're looking for. The local max, top of a little hill, local min, bottom of a little cup, right? And so that's what we're trying to ultimately get to. So where we start is what's called a critical point. So a critical point P for a function is a point within the domain where the derivative at that point equals 0. So we're looking for the points where we have horizontal tangent lines, or a place where the first derivative is undefined. So when does that usually happen, right? So if we have a function that has a denominator and that denominator is 0, then that would be a place where it's undefined. So when we're looking for critical points, we're trying to figure out where does the first derivative equal 0 or where is the first derivative undefined, okay? A critical value is the y value that goes with that x value, right? So the actual whole entire point, like x comma y, you would have the critical point comma the critical value. Typically, we're just looking for the x value for the critical point, but just in case it comes up in Wiley, the critical value is the corresponding y value. So that's sort of where we start. How do we start to find these critical points? Okay, so we're going to start with some examples of finding critical points. And once we get comfortable with that, then we'll be able to circle back and figure out how do we determine if these critical points are local maxes or mins. So we'll do one together to start. So here we have the function 3x squared plus 6x plus 1. And we want to find the critical points. So we know that critical points happen when the first derivative equals 0 or when it's undefined. So we find the first derivative. So here we're going to get 6x plus 6 and then plus 0 because that will go away. And we want to know, when does that equal 0? There's no denominator here or anything that would lead me to something that's undefined. So I really only have to check if it equals 0 in this case. So I bring the 6 over, I get 6x equals -6, divide both sides. And here I have a critical point at x equals -1. So what that tells me is for this particular function, that at -1, I'm going to have a horizontal tangent line. Okay, I don't know yet if it's a local max or a min, but at -1, I have this horizontal tangent line. Okay, so I want you to try these next two. For number 2, you will have to factor this to figure out where it equals 0. And for number 3, you do have to use the quotient rule. So you do have to consider when it equals 0 and when it's undefined. Okay, I'm going to give you about 3 minutes to try out these two problems. We're trying to find the critical points, so the x values that make these 0 or undefined. So try it out, try to think back to your algebra, and then we'll go through it together. All right, take about 30 more seconds. All right. So for example 2, again, for critical points, we want to start by finding where the first derivative equals 0. So here we go through our regular derivative rules. So we have 6x squared minus 6x minus 36. And then the 14 goes away because it's a constant. And we want to know, when does that equal 0? So there's 2 ways to approach this algebraically. We could use the quadratic formula or we could factor. Either way, you should get the same answers. So I'm going to factor. So first I'm going to pull out the 6 just to make the factoring a little bit easier. That's just a preference for me. You may have factored slightly differently. So I'm looking for 2 numbers that multiply to give me -6, but add up to give me -1, that cross term. So I get 6 times x minus 3 times x plus 2. And I want to know, when does that equal 0? So I look at each of my factors and think about what value would make it equal to 0. So for my first factor, if I solve that, I get x equals 3, we'll make that 0. And from my second factor, I get x equals -2, we'll make that 0. Right? So if I set 6 equal to 0, there's no solution. So I have 2 critical points here, one at x equals 3 and one at x equals -2. Okay? For example number 3, I notice that I have one function over another function. So in order to do my derivative here, I'm going to have to do a quotient rule. So over here on the side, my top function is my f, my bottom function is my g. I find the derivative of each respective piece. The derivative of x squared is 2x. The derivative of x minus 2 is 1. So now I'm going to plug this into the formula, right? Oh, my prime is missing here. So f prime times g. So I have 2x times x minus 2 minus g prime times f, all divided by g squared. Okay, now before we weren't super concerned with simplifying, but now we are, because now we want to use this derivative to solve. So I'm going to take a step here to simplify my numerator. I'll probably do it in 2 steps. So here I want to distribute the 2x. So I have 2x squared minus 4x minus x squared. I'm going to leave the denominator as is for now. And now that I've distributed the 2x, I notice that I have a 2x squared and a minus x squared. So I can write this as x squared minus 4x over x minus 2 squared. Okay, so this is nice and simplified. And so now I want to think about how to answer the question, when does the derivative equal 0 and when is it undefined? And I'm considering undefined because here I do have a fraction with a denominator. That's not something I've had before. So when does the derivative equal 0? Okay, so f prime of x will equal 0 when the numerator equals 0. So if the top part equals 0, then the fraction will equal 0. So I can isolate that numerator and I can factor it. So I pull out an x and I'm left with an x minus 4 equals 0. So here I'm thinking again about each factor. So here, since I have an x, one solution is x equals 0. And then I think about my second factor, x minus 4. So a second solution is x equals 4. So x equals 0 and x equals 4, both solve this. Okay, so that's 2 critical points because that's going to be when my first derivative equals 0. Now my first derivative will be undefined. The second choice I have, when the denominator equals 0. Okay, so I also have to consider that. So x minus 2 squared, that will be 0 when x equals 2. So that's another critical point here. So I have 3 critical points, 2 from when the derivative equals 0 and 1 from when the derivative is undefined. So we have x equals 0, x equals 4, and x equals 2. Okay, so hopefully you found all of those. And again, hopefully you see that we're going to be relying on your knowledge of the derivatives from chapter 3 to help move us through chapter 4. Okay, so these 3 examples are all algebraic. So we had algebraic functions that we were then using and doing these rules too. But we can also think about critical points in other ways, right? So graphs and tables are other ways that we often present information. So let's look at some examples where we are not doing it algebraically to make sure that we can apply sort of the same ideas, okay? So suppose that f prime of x is given in the graph below. Use the graph to determine the critical points of f of x on the given interval -2 to 8. So that's what we see here, -2 to 8. What's important here is that this is a graph of the first derivative, okay? It's going to be really important that we always understand what type of information we are given. So we could have a graph of the original function. We could have a graph of the first derivative. We could have a graph of the second derivative. And that's all going to change how we look at it. So here we are given a graph of the first derivative, and we want to use that to find the critical points of the original function. We don't have the original function. We don't know what the original function looks like. So here, all we can do is we can use what we know about critical points to work with this first derivative graph. So we're going to have critical points when the first derivative equals 0 or when the first derivative is undefined. Okay, there's nowhere on this graph that's undefined. It's a continuous graph. There's no asymptotes. So this doesn't really apply here. We can, however, figure out where the first derivative equals 0. This is the graph of the first derivative. So we're literally asking, when does this graph equal 0? So when is the y value 0? So that's going to happen whenever we cross through the x-axis. So it looks like we have 3 critical points here, one at 0, 0, one at 3.1, and one at 6.2. Okay, so that's how we find our critical points of the original function. We consider when the derivative equals 0, which we have to understand how to look at on a graph. Okay, so those are our 3 critical points. So x equals 0, x equals 3.1, and x equals 6.2, roughly. Okay, so those are the 3 critical points here. Similarly, suppose that we have a table, and the table gives us some values of the first derivative. We want to use that to think about where the critical points of the original function are going to be. We also know that the original function and the derivative are continuous, which means that they are going to keep going between these points. There's nothing super crazy happening between them. So we need to look at this table of values for the first derivative and think about where we might have critical points. So take 1 minute just to look it over. See if you can think about where any critical points may be. And I will tell you, one is meant to be more obvious, but there's actually 2 places where we're going to have critical points. So take a look at that for just 1 minute, and then we'll review how we figure that out. Okay. So again, the information we have is about the first derivative. And we know that critical points happen when the first derivative is 0 or undefined. There's nothing here to indicate undefined. So we're really thinking about where will the first derivative equal 0? Well, one of them is given to us. Literally, we know that at x equals 6, the first derivative equals 0. So that is a critical point, right? When the first derivative equals 0. So when I think about the other values, however, -14, -8, -4, right? Those are all negative. Then I go through 0, then I have 5, then I have 2, and then I have -1. So what I want to point out here is that somewhere in here, I went from +2 to -1. In order to go from a y value that's positive to a y value that's negative, right? So let's say 2, and then, right, -1. In order to connect a positive y value to a negative y value, I have to go through 0, right? In order to change signs, I have to go through 0. So I also have a critical point between x equals 10 and x equals 12. Now, I don't know exactly where it is. It might be at 11, but it might be at 10.5. I don't know. But I have to cross through 0 somewhere in here in order to change from positive to negative, right? To cross through the axis. So there's one hidden in here. So the way we look at tables is we look for zeros on the derivative, but we also look for places where we change signs. Okay, we also change signs here around the 0, right? Negative to positive, but we know exactly where it happened. Here, we don't know exactly where it happened, but we do have to pass through 0. So that's how we think about this on a table. Okay, so now that we know how to find critical points, the next step is to take that information and say, okay, once we have identified where the critical points are, how do we determine if they are local maximums, local minimums, or neither? Okay, so we're going to take this critical point information and we're going to learn how to what we call classify the critical points. And there's 3 different ways that we do this. And so we're going to look at each test, each of the 3 tests, and how and when we might use it. But part of it is also just getting used to looking at these types of problems. I will tell you that there's a lot more problems posted on the different tests on Moodle because we just don't have enough time to go through all the examples. So if you want to see more examples of any of the tests, you can look at the videos on Moodle and sort of go through them there, okay? So let's start with this function, 4x cubed minus 6x squared minus 72x plus 12. We want to figure out the critical points and then figure out if they're local maximums or local minimums. So the first step before we even apply a test would be to find any critical points of this function. And so we'll sort of do that on the side. Okay, so the derivative here is going to be what? It's going to be 12x squared, right? The 3 comes down to multiply the 4, minus 12x minus 72. I want to know, when does that equal 0? So I'm going to pull out the 12. So I have x squared minus x minus 6 equals 0. So I have x minus 3 and x plus 2. Okay. So we have x equals 3 as a critical point. Oh, and x equals -2 is a critical point. Okay, so that's always the first step. We got to know where the critical points are, and we'll look at this a bunch of different ways. But here, the first test we're going to use is the original function, right? So if we have information about the original function, what we can do is we can look at where the original function is increasing and decreasing around the critical point to figure out what type of critical point it is. So what does that mean? That means we want to look at what's happening at 3. Okay, so we see the critical point, and we want to look at what's happening at -2. Okay, and we are literally graphing our function with this test to see if it's increasing or decreasing around the critical point. So if we look at -2, we see that to the left we are increasing, and to the right we are decreasing. We can see very visually that this is a local max because it's this hill. Okay, similarly, if we consider what's happening at 3, we can see that we start off decreasing before our critical point and increasing after our critical point. So if we go from decreasing to increasing, that makes it a local minimum. Okay, so what type of information do you need to have to use this first test? You would need to have information about the original function, and then you would be able to graph it to see what was happening. Now, this seems silly because if you look at it and you're like, yeah, I can see that it's a local max or a local min, that's sort of the point. So if you can graph it, you can tell what type of critical points these are going to be. Now, this isn't the only way we're going to use this test, but when we talk about it algebraically, graphing it is a really good idea, right? You have your critical points, you can look at it, tell if it's a max or a min, but very specifically, what the test says is if f of x changes from increasing to decreasing, so going up and then coming down around your critical point, then that critical point is a local maximum. If the function changes from decreasing to increasing around that critical point, you're going to have a local minimum, so you go down and then up. And then if f of x does not change, then it's neither. So very quickly, what does it mean that it does not change, right? We don't have that in this example, but let's say you had a graph that looked like this, okay? So you would have a local minimum over here, but you would also have a horizontal tangent line right here, okay? So you're gonna have a critical point here, but this is not a local max or a local min. It kind of just flattens out for a minute, right? So you can kind of see it's like not really either. And so in that case, this is a situation where you would have a critical point, but it's not a max or a min. So that's what a neither case looks like, okay? So let's start with this example here. What I want you to do is I want you to find the critical point of this function. Then I want you to graph the original function, either if you have a calculator or you can pick a couple points to get a sense of what the graph looks like, and use the graph to decide if that critical point you found is a local max, a local min, or neither. Okay, so I'm going to give you about 2 minutes, try it out, and then we'll go through it together. All right, take about 30 more seconds. All right. So again, we want to start by figuring out where our critical points are. So we're going to start by using first derivative. So here we're going to get 6x plus 6 as our first derivative. We want to set that equal to 0. We bring the 6 over and divide, and we get a critical point at x equals -1. Okay, so that's one that we did before. But now we want to figure out, is it a local max or is it a local min or is it neither? And so we go back and we graph the original function to think about what that's going to look like. And so when you graph it, you're going to get something that looks roughly like this. Okay, so at -1, which is going to be over to the left of the origin, what you'll see is that we have a cup shape, right? So this is a parabola that opens upwards. And so looking at this, I can see that I'm going from decreasing to increasing. And so if I go from decreasing to increasing, that makes my critical point a local minimum. Okay, so using the graph is definitely helpful, but what you need to remember is that you need to graph the original function, but you have to use the critical point, which we found from the first derivative. Okay, so here we have a local minimum. How else might we use this set of rules? Okay, so the other way that this comes up is in an example like this. So I'm going to talk about it for a second and then have you think about it. So f of x and f prime of x are continuous, so they are connected everywhere and differentiable. We also know that f of x has a critical point at 5 and 11, okay? So the original function, we have a critical point at x equals 5 and x equals 11. Use the table of values below to determine if these critical points are likely to be local maximums or local minimums. So I want you to think about this for a minute. So 5 and 11, think about how you might use those rules to classify these two critical points. So I just want you to take a minute, look at the values, see what you think, jot down whether you think they're going to be local maxes or mins, and then I'll go through it, but only take 1 minute here. All right, so let's think about this. So this particular test has us looking at what's happening around the critical point. So that means before we get to the critical point and after. So if we think about this, this is the original function, and we look at these values, 4, 8, 10. So these values are increasing as we get from left to right towards 5. Then after 5, we have 8, 5, 2. So these values are decreasing. And then to the right of 11, we have 7 and 10. So those are increasing. So here what we see is that our function is going from increasing to decreasing around 5. So if we are increasing to decreasing, we have a function that looks like this, which makes 5 a local max. And then here at 11, we're going from decreasing to increasing. So we're going down and then we're going up. So that makes this a local min. Okay, so that's how we might use those rules in this type of scenario to really think about whether we have maxes or mins. Okay, so that's our first test. The second test is what's called the first derivative test. Okay, and so again, before we even use the test, we need to know what the critical points are. This is the same function that we just looked at for the first test. So I'll quickly just remind you what the critical points were, and then we'll talk about the test. So we had 12x squared minus 12x minus 72. We factored out the 12. We had x squared minus x minus 6. We wanted to know, when does that equal 0? And so we have 12 times x minus 3, x plus 2 equals 0. So our critical points are x equals 3 and x equals -2. Okay, so that's our first step. We need to get our critical points. So now another way that we could classify these. So the first time we just looked at this, we just looked at the graph, right? And looked at what was happening at 3 and -2. Another way we can look at this is within the first derivative. So what does that mean? Okay, so here we have the critical points divide the domain of f of x into intervals, which the sign of the first derivative remains the same for the duration of that interval. So what that is telling me here is that I can set up an interval divided by the critical points. So -2 and 3. So this is a number line, right? These are x values. And what this is telling me is that I'm going to use the fact that at -2, the derivative is 0, and at 3, the derivative is 0, to create intervals. So my intervals here are going to be -∞ to -2. That's this first interval. -2 to +3 is the second interval. And 3 to infinity is the third interval. The critical points will divide up where the function is doing different things, basically, is what's happening here. So now my first derivative test says if the derivative changes from positive to negative around the critical point, we have a local max. If it changes from negative to positive, we have a local min. So what does that mean? I need to know the sign in the interval. Is the derivative positive or negative in this interval? Is it positive or negative in this interval? Is it positive or negative in the third interval? The good news is it's the same sign for any point on the interval. So what I do is I pick a test point, okay, for each interval to figure out what the sign is going to be. So you want to pick your test point to be something easy to work with. So for this interval here, I'm going to pick -3 to represent my interval. And so I take my -3 and I plug it into the derivative to see if the sign will be positive or negative. So when I plug it in here, if I plug in -3, I get +72 is the value. But what I'm really interested in is the fact that it's positive. I need to do a test point on the interval -2 to 3. So I'm going to pick 0. 0 is an easy thing to plug into my derivative. My test value gives me -72. I'm really interested in whether it's positive or negative, so I'm going to highlight the negative. And then I need to do a test point over on this interval from 3 to infinity. So I'm going to pick the number 4. Again, you could pick 5, 6, 7, any number between 3 and infinity. So if I plug in a 4 here, I plug it back into the derivative to figure out the sign. I again get +72. So for this interval, I am positive. Okay. So again, those test values just help you highlight the sign of each interval, because our test now is going to help us understand whether our critical points are maxes or mins. So if the derivative changes from positive to negative around a critical point, we have a local maximum. So we see that that happens at -2. We change from positive to negative around the point. So that makes this a local maximum. Okay. And at 3, we see that the derivative goes from negative to positive. So if your derivative changes from negative to positive around a critical point, that's going to give you a local minimum. So 3 is going to be a local minimum. So that's how we can use the first derivative to classify our points. And what I want to remind you, let me find the picture here, is that this agrees with what we did before, right? So at 3, we had a minimum. At -2, we had a maximum, right? At 3, we have a minimum. At -2, we have a maximum. These are 2 different tests to get the same information. So if you use the first derivative test to classify your critical points, you can still graph the original function to check to make sure you did it correctly, okay? This is the same function, we're just using 2 different tests to classify. Now you might have a preference of one test over the other, and sometimes you don't have a choice, but if you do have a choice, you can do it either way. You will get the same information, okay? So now I'm gonna have you try this one. You're gonna do it similarly. You'll notice a pattern here when you work this out, but I want you to take the first derivative, find the critical points, then you're gonna set up a number line and you're gonna look at how it changes in the different intervals, okay? So take 2 minutes, see if you can get that set up, and then we'll go through it together. All right, take about 30 more seconds. All right, so again, we have to start by finding our critical points so that we can then set everything up to test them. So we find our first derivative here, which is going to be 6x squared minus 6x minus 36. We want to know, when does that equal 0? So if you factor out a 6, you're left with x squared minus x minus 6. So again, we can factor that down and it becomes 6 times x minus 3 times x plus 2. That gives me critical points at 3 and -2, which is the same critical points I had before, even though this is a slightly different function. And so I want to draw a number line and I want to put my 2 critical points on there. So we have -2 and 3. These are the critical points that we are trying to classify. Okay, and so we know that the derivative equals 0 at these points by definition, because they're critical points. So we need to pick some test values for each interval. There's 3 intervals here to figure out how we are changing around these points. Now, last time I said you could pick a test point and plug it back in to get the value. I do want to point out that you can also reason through this without plugging in if that's your preference. So I just want to talk about how you might do that. So I'm going to use the same test points just because they're convenient. But again, you can pick any number on the interval. So for -3, I can look at the factored version and think about whether or not each factor will be positive or negative. So like -3 minus 3 is -6. So that's negative. -3 plus 2 is -1. So that's negative. So negative times negative is positive. So I can reason through like that. If you don't want to plug it back into the full derivative function, you can just look at what the signs of the factors will be to figure out the sign for the interval. So if we did the same thing for 0, 0 minus 3 will be negative, because that'll be -3. 0 plus 2 will be 2. So I have negative times positive is negative. And then for the number 4, 4 minus 3 is positive, 4 plus 2 is positive, positive times positive is positive. So you can also do it that way. It's really a matter of preference. If you would prefer just to plug it into the first derivative to get the value and then say whether it's positive or negative, you'll get the same results. So here again, when we go from positive to negative, that's going to make this critical point a local max. And then here for our second critical point, we go from negative to positive. So if we go from negative to positive, we have a local min. If the sign does not change, then it is neither. So if we had like negative to negative, it would be neither. Okay?
Hey, Dina,
Yes.
you actually froze for just a second there. Can you repeat that last thing?
What was the last thing you heard?
Oh, you said like if it switches from positive to negative.
Oh yeah, so if it goes from positive to negative, then we have the local max. If it goes from negative to positive, we have a local min. It would be neither if you went like negative to negative, like if the sign did not change, that's when we have neither. Okay, so now we want to think about how we might be able to use this first derivative test with graphs or with tables. So I'm going to have you look at both of these. I don't know if I can have them on the screen at the same time. So let's just read them. So the derivative function is given in the graph. So this is f prime of x. We want to use this to find any local maximums or minimums of the original function. So for this one, we'd have to find critical points first, which we already did for this graph. We found the critical points. But now we want to figure out whether they're local maxes or mins based on the first derivative test. So if they change from positive to negative around the critical point, local max. Negative to positive, local min. Similarly, we're going to look at the same thing on the table. This is the same table we looked at before. So we know how to find the critical points. We had one at 6 and one between 10 and 12. But now we want to classify those critical points using this test. Okay, so I want you to take 2-3 minutes. First, label all your critical points, and then think about how we can use that first derivative test to classify them as local maxes or local mins based on how they change signs. Okay, so take about 3 minutes. I'm going to fill up my water bottle, so I will be right back, and then we'll go through it together. right, so let's take about 30 more seconds. All right, so let's start with the graph. So again, we want to know where the critical points are, which is going to be where the first derivative equals 0. So here, here, and here, because again, this is a graph of the first derivative. But now we want to figure out what type of critical points these are. So again, what our test says is we want to look at how the sign changes around the critical points when we have the first derivative. So here, to the left of our critical point, our function is positive because it is above the x-axis. To the right, it is negative because it is below the x-axis. So we go from positive to negative, and the test says if your derivative goes from positive to negative, you're going to have a local max. So remember, this is telling us where the local maximum is on the original function, which we don't have. We don't have a picture of it. We don't know what it looks like, but we do know that there's a local maximum at x equals 0 on the original function. Okay, so now when we look at the next critical point, we see that it goes from negative to positive, so below the x-axis to above. So that means, according to our test, that this critical point is going to be a local minimum. So again, that means there's a local minimum on the original function. And then finally, our last critical point, again, positive to negative, because we're going from above the x-axis to below, which is going to be another local max. Okay, so when we have a picture of the first derivative, we are looking at how the sign changes as we go through the 0. That's going to tell us whether we have a local max or a local min on the original function. Similarly, if we have a table, again, we start by finding our critical points. So we know that there was one at 6 because the derivative equals 0 there. And we know that there's one between 10 and 12. Right? And so now we need to look at how the derivative changes. So here, I went from negative to positive around this critical point. So if you go from negative to positive, that makes your critical point a local minimum. And then for our second critical point, we're going from positive to negative, right? So wherever it is in here, we started off positive to the left of our critical point and ended negative. So that tells me I have a local max. So again, if you are given information about the first derivative, then you sort of have to be pigeonholed into the first derivative test, right? The first example that we looked at was algebraic, so we had some flexibility in choosing. But for these two examples, we don't really have a choice because the only information we have is about the first derivative. So we're thinking about how we change signs around the critical point in the first derivative, okay? So now, third, last but not least, we have the second derivative test. So it's our third and final test for classifying critical points. So we've used the original function, we used the first derivative, and now we're saying that there is a way to use information about the second derivative to classify critical points. So again, we go back to our function that we've looked at for all of our tests, 4x cubed minus 6x squared minus 72x plus 12. The first step we know is finding the critical points. 12x squared minus 12x minus 72 equals 0. Again, this is the same one we've been looking at. So I'm going to do this kind of fast.
Hey, Dina?
Yes.
You froze again.
Okay, so I was just saying this is the same function that we were looking at before. So this first part is the same as what we've been doing. So here are critical points, x equals 3 and x equals -2. Okay, so this is the same function that we had started with for the first two tests that we checked out. So this first setup is the same to find these critical points. So now what this test is saying is that we can use the second derivative to classify these critical points. So as a reminder, we already classified them with the first derivative test by making a chart and the original function test by graphing it. So we already know what to expect here, but how do we use the second derivative? Well, let's find the second derivative function here. So we go back to the unfactored version of the first derivative to make this easier. And we get 24x minus 12. So our second derivative is 24x minus 12. So what I want to remind you is that if the second derivative is positive at any point, we know that it's concave up at that point, back from when we looked at concavity in chapter 2. And if the second derivative is negative at a point, that means it's concave down at that point. Okay, so what that does for us is we can plug our critical point into the second derivative and figure out the concavity of the original function, which will tell us if it's a max or a min. So there is a typo in the notes that if you have printed them, you'll want to fix it. But if the second derivative is positive at your critical point, then we are concave up, and then we know that our critical point is a local min. If the second derivative is negative at your critical point, then we know the function is concave down, which makes your critical point a local max. And if your second derivative was 0 at the critical point, then it would be neither. It would be an inconclusive test. Okay, so how do we apply that here? So we have the second derivative and we have our critical points. So we want to plug these in to the second derivative. So if we plug in a 3, we have 24 times 3 minus 12. We would crunch that number and we would get 60. Okay, the 60 is not what's important. What's important is if it's positive or negative. So here, this is positive. So since the second derivative at 3 is positive, then the original function is concave up, which tells us that our critical point here, this x equals 3, is a local minimum. So I'm going to write that up here. Okay, we can perform the same test for our other critical value, which is -2. I'm going to do it up here because I've run out of space. So if we plug in a -2, we have 24 times -2 minus 12. That gives us -60, and it's the negative that's important. So the second derivative at -2 is negative, which tells us the original function is concave down, which makes -2 a local maximum. And again, this agrees with the other two tests that we've done on the same function. So if I were to use the second derivative test, right, to classify these, I could again graph the original to make sure that it matches what I have found algebraically. Okay, so I want you to go ahead and try this next one. So we have 3x squared plus 6x minus 1. I want you to find the first derivative to use to find the critical point, and then use the second derivative to classify the critical point using these two rules. Okay, I'm going to give you about 2 minutes. Try it out. This is an interesting problem that has something interesting happen, so hopefully you can figure it out, and then we'll go through it together. right, take about 30 more seconds. All right. So again, we start by finding the critical points. So my first derivative here is 6x plus 6. We set that equal to 0. We solve for x, and we get x equals -1. So our critical point is x equals -1. If we want to use the second derivative test here, we look at the first derivative and we say, okay, the derivative of 6x is 6, and the derivative of 6 is 0. So the question becomes, can I still use the second derivative test if I can't plug in my critical point? And the answer is yes. So if your second derivative is a constant, that still tells you the concavity of the original function. So since this is positive 6, it's positive for all x values, including -1. So if your second derivative is positive, that tells you the original function is concave up everywhere, including -1, which means that this critical point has to be a local minimum. Okay, so if your second derivative has the variable in it, like we saw in the last example, you need to plug your points in. If it doesn't have the variable in it, you can still use the sign to make the final determination about your critical point. Okay, so don't let that throw you off. You can still use it. All right, so let's look at some other ways that we can use the second derivative test. I think for now, we're going to skip number 4. We'll see if we have enough time, but that one is also algebraic. The function is just a little bit harder, but it's the same as the last two we did, whereas 5 and 6 are a little more conceptual. So what I want you to do is I want you to look at these two problems and see if you can figure out how we might use the information and the derivative tests we've been talking about to answer these questions. So for number 5, you're given 8 different pieces of information about the function, about the derivative, and about the second derivative. And you are trying to figure out if we have any local maximums or minimums that we can identify with that information. And for number 6, we're asking the question, what constraints or what needs to be true about A in order for this function to have a local minimum? So I want you to think about what the first derivative of this function might look like and the critical point, and what the second derivative might look like, and if we can use either of those to figure out anything about A. Okay, so I'm going to give you about 3-4 minutes, since these are a little more conceptual. See what you can figure out, and then we'll go through them together. All right, take about 30 more seconds. All right. So starting with example number 5, let's think about the type of information we have. There's sort of 3 categories. We have some information about the original function, we have information about the derivative, and we have information about the second derivative. So we were asked to figure out if we could determine where we might have local maxes and mins. So we know from before that we want to start by looking for critical points. So places where the first derivative is 0 or where the first derivative is undefined. So there's nothing here that's undefined. So what we're looking for are places where the first derivative equals 0. So from our list, we have f prime of 4 equals 0 and f prime of 9 equals 0. So that means that at x equals 4 and at x equals 9, we have critical points. So now we need to figure out what we know about 4 and 9 to figure out what type of critical points these are. If you look at the information we have for f of x, we don't have enough information to determine if we are increasing and decreasing around these points. We'd have to have a lot more data points to figure that out. If we wanted to use the first derivative test, we would need to be able to find something to the left of 4 and something to the right of 4. We have a value to the left of 4, right? We have 2, which is positive, but we don't have something to the right of 4 because this is also 0. And in order to use the first derivative test, we would need something between 4 and 9, which we don't have. So we look to the second derivative and we see that we have values at 4 and 9 within the second derivative. So we can use the second derivative test here to classify what's happening at 4 and at 9. So at 4, the second derivative is negative 4. If the second derivative is negative, the original function is concave down. So that tells us that x equals 4 is a local max, right? Because we're going to be right at the top of that concave down situation. At 9, we see that the second derivative is positive 3. That tells me that the original function's concave up at 3, which makes, or at 9, I'm sorry, at 9. So at x equals 9, we have a local minimum, okay? So we're using the values of the second derivative to determine the concavity for the critical points. But again, the critical points are 4 and 9. It's the x values that we're plugging in. So we were able to use the second derivative here to classify these places that we identified as critical points. All right, so for example 6, we have ax squared plus bx minus c, where a, b, and c are all constants. So if we think about what we know from the first derivative, we're going to look here. If a is a constant, then the derivative will be 2ax. So the derivative, the a stays there because it's a constant multiple. From the second term, the derivative of bx is b, and then the derivative of c is 0. So this is what our function looks like. If we were looking for the critical point, we would set this equal to 0 and solve for x. So we would subtract b over and then divide. And we would get x equals negative b over 2a. That's our critical point. But that doesn't help us ensure that that critical point is a minimum, right? We're trying to figure out what will force this to be a minimum for us. So what we do now is we think about the second derivative. And we get that the second derivative is 2 times a. So thinking back to the example we did a minute ago, where the second derivative equaled 6, and we said that would still tell us what our critical point was doing, we want to use something similar here. So there's no x in our second derivative, which means that whatever value this takes on will tell us the concavity of the original function. So if 2a is positive, the original function will be concave up. If 2a is negative, it'll be concave down. Well, we want it to be concave up because we're looking for a local minimum. So we want 2a to be positive. In order for 2a to be positive, we would need a to be greater than 0. Okay, so if a is greater than 0, that ensures that the second derivative is positive. If the second derivative is positive, that ensures that our critical point is a local minimum. If we were to switch this and ask for it to be a local maximum, then that would change that a would have to be less than 0 for the same types of reasons. Okay, so again, if you're looking for more examples of any of the 3 tests we talked about today, please look over the videos that are posted on Moodle. Otherwise, start the homework early. There's a lot of algebra in this so that you can get help if you need it. Okay, I will see you all on Thursday. Have a great rest of your afternoon.